So we left off talking about this generic mechanism for alcohol conversion, and talked about it being a substitution, and the fact that the OH group in that substitution is what's going to leave, and it's going to get replaced by a halogen, which is in this case a nucleophile. So let me talk about that just for 1 second. Right, so in a substitution, I'll just keep using the same. Right, there's some basic things that we need to understand about that, going forward. And the first thing is that the substitution always involves what we call a leaving group. So the leaving group is usually, how do I put it, highly electronegative. And it's usually a good conjugate base. All right, and then so when that substitution happens, you have we're going to talk in a lot more detail about substitution in about a week or so, maybe 2 weeks. So you have a substrate. That substrate contains the leaving group. And then you also have a nucleophile. These terms should be familiar to you from part 1. All right, so it's the nucleophile in a substitution that replaces the leaving group. Now, how it does that depends on the type of substitution. If it's SN1, the leaving group leaves first. If it's SN2, then it's simultaneous. The nucleophile attacks and the leaving group leaves. So let me show that. So if it's SN1, there's a step that involves the loss of leaving group, excuse me. You end up with a cation, and then your nucleophile attacks that. Nucleophile is going to attack here. And then your product, this is your substitution product, where the nucleophile is here and the leaving group is still present. It normally makes a salt with some whatever the nucleophile counterion is. It'll make a salt with that. So that's that. If it's SN2, need more room. Right, it was SN2 is concerted. So nucleophile is going to come in and attack at the same time that the leaving group is leaving. So this is going to come here. The leaving group is going to leave. So you end up with the same outcome, just a different mechanism. So nucleophile replaces the leaving group, but it's all considered substitution because you're swapping out one functional group for another. So you're actually, in this case, swapping out the leaving group for the nucleophile. So all these reactions that we look at today are going to involve some type of substitution, and they're all going to involve a step where you have to take the hydroxyl group of the alcohol and make it a better leaving group in order for it to facilitate the reaction. All right, so hopefully you have this handout. I did send an announcement for you to grab it. I also put it in the chat the other day, Wednesday. I'll put it in the chat, so you should have it. All right, so the first reaction that we're going to look at is the reaction of, or the conversion of an alcohol to an alkyl halide using thionyl chloride, right? So thionyl chloride is this species right here, SOCl2. It's a very good electrophile. And so remember I told you that in order to do certain transformations, you need certain tools, right? So here, the tool is thionyl chloride. But just like everything, every tool doesn't work on every substrate. So there are some things about this reaction that are important. And the first is that this is specific for primary alcohols. Right? You can probably get away with it with a secondary, but it'll be a little bit slower because of the way that the substitution happens. But typically, if you have a primary alcohol and you want to convert it into an alkyl halide, you'll use this thionyl chloride, right? And what I don't have here, if you were to see this written out, the arrow would look like this. So we have SOCl2 and then pyridine underneath the arrow. All right, so this is pyridine here. Right, pyridine is a base, a very good base, and it will facilitate the reaction by making the oxygen of the alcohol more reactive, right? Because it's going to have to do an addition in the next step. So in order to do that, let me just fix this so we can see the arrows. Wipe that out. Right. So the first step is proton transfer to pyridine. All right, so pyridine is going to donate this pair of electrons here. It's just an acid-base reaction. And then that's how we get to this step. You can see here, now oxygen is fully deprotonated and is negative. All right, it has a formal charge of -1. And then my pyridine is here. You can see that too. So now we have this, with the nitrogen being positive, we call it a pyridinium ion. All right. So that first step is simply to make oxygen more reactive. And then that's when we introduce the thionyl chloride. Now, normally, if you were doing this, like if we were up on the 3rd floor running this reaction, you would probably stir your alcohol with pyridine for a few minutes and then just syringe in the thionyl chloride very slowly. That thionyl chloride is highly reactive, even with the water in the atmosphere. So you'll have to syringe that in slowly, and then the reaction will take place as we have it depicted. So how do we get from here with the oxygen, negatively charged oxygen plus thionyl chloride, to here? How do we get there? What I'm asking for is, what arrows would you add to show how we get to that intermediate? You can see over here that there's a new bond between oxygen and sulfur, right? That same oxygen right here and this sulfur right here. So how would you show that bond being formed? Don't break the internet by all speaking at once now. Like, how would you show any bond being formed in organic? between a nucleophile and an electrophile?
Don't use arrows.
You got to use curved arrows. Same way we did over here, right? So this step right here is going to be an addition, right? You can't do substitution on an sp2 hybridized atom, and the the sulfonyl functional group is the sulfur is sp2 hybridized. So this is going to, and because of that, it has a pi bond present. And so anytime you're adding to a pi system, it's not, you can't substitute directly. You have to do what we call addition followed by elimination. So in this case, I'm going to attack here. What do I need to do to the pi bond in order to get to this intermediate right here?
You have to break it.
Got to break it, right? And give the electrons to oxygen. Keep in mind, even though I don't have it shown, oxygen had two lone pairs already, right? So over here in the intermediate, this is the same oxygen right here. I just have it drawn, oriented differently, but it's the same oxygen. All right, questions up to this point. So you have a proton transfer, you have an addition, right? And then you form this intermediate one. And then,
I did have a question.
go right ahead.
The very first one where how did we lose the hydrogen again? What did we add to the solution?
Pyridine.
The pyridine. Okay.
Yeah, it's a proton transfer. So pyridine is a base, and all alcohols have acidic properties. And so the pyridine is just going to attack that proton and pull it off.
Okay, thank you. Sorry.
Good question. So now you have intermediate. I'm just going to call it intermediate one. Okay, so now look at what happens. We go from intermediate one. We're going to call this intermediate two. What did I do? What changed? Look at the two species and tell me what's different about the one on the right. Intermediate two, what's different?
The oxygen is now a double bond to sulfur.
Okay, so I have a double bond between oxygen and sulfur. I reestablished that. And then what else happened? You're right.
Chlorine was kicked out.
Kicked off of chlorine, and my apologies that this does not have a negative sign, but it is negative. So you can fix that on the handout as well if you're working on it. So I'm going to do this, take this pair of electrons, push them here. Keep in mind, I don't have the lone pair shown, but chlorine has 3 lone pairs, right? So I'm going to kick that here like that. And then that'll get me the intermediate 2 and then the chlorine. So now this is important because the chlorine here is now my nucleophile. That's my nucleophile for the next step. And if you look at a product, which is right here, that's my product. What do you think happens? Now this part, so we did an addition, the step where we lost chlorine, we call that step is an elimination. Come on, Russell. That's an elimination. And then now this is the substitution part. All right, so it's really three different types of reactions happening within this mechanism. So you had an addition, you have an elimination, and now this part here is the substitution to go from intermediate 2 to the product. How do you show that? What happened? Let me write this here, because this is a side product. And then we still have this pyridinium here. All right. Those are side products that end up in the trash, in the waste. So it doesn't matter. We don't care about that. We only care about how we got from intermediate to the product. So what do you think? Look at what's now in place of this group right here, which is my leaving group. So this is my leaving group. All of that, all of those steps to get me here, where now oxygen is a better leaving group than it was when it was OH. So we did all of that to get to here. So we can get rid of the leaving group and substitute it with the halogen. All right. So somebody help me out. Tell me what you would do to show the halogen coming in and the leaving group leaving. Don't worry. Okay, come on.
Let's say, because that's a lot.
So
I always thought you couldn't break a single bond. I'm not a single bond, but like, so,
oh, you can break it.
okay.
If we could, and don't take this the wrong way, if you couldn't do that, chemistry wouldn't exist, right? You got to be able to break it. But the way you show that, and every bond is not equally breakable. Some bonds are stronger than others, right? But the way you show it is your nucleophile, right? If this is my nucleophile, the chlorine, and this is my substrate up top with the leaving group attached to it, I just need to show, and this is the carbon that I'm going to react on right here. Right? I just need to show how that happens. So you can definitely break that bond. That's actually an easy bond to break because the sulfur and the oxygen, that's a pretty and that sulfur, well, the sulfonyl, the S double bond O, that's polarized, and so it's going to be pulling electrons away from that oxygen, and it's going to make that bond very easy to break. So we're going to attack it here, boom, like that, and then we're going to break this bond and give those electrons to oxygen. That's how we get here.
We got it. And then what happens to the SOCl2? Does it just now have a charge?
Well, yeah. So up here is not SOCl2, right? It's just SOCl. So that's here, right? And then the pyridinium is also still here. Now there's probably another step in the reaction where these two get married and they do some swapping, right? So you end up with pyridine back by itself and neutral again, which is good, plus HO S double bond O Cl, right? So you probably do have a point in the reaction where that happens, but I never focus on that because I always just, you know, I'm all about getting to the product, right? But that will happen because in chemistry, nothing wants to stay charged, right? Your atoms want to be neutral. They want to have an octet. They want to meet the octet rule and be neutral. So between the pyridinium and the sulfonate anion, they'll probably do some acid-base chemistry, do a proton transfer, and then everybody's happy after that. I'll even write that in down here, proton transfer. All right. Questions about that? Anybody? Nothing in the chat. Again, if you are having problems with the arrows, we need to address that. So that's something that we can talk about, maybe not necessarily during the lecture, but after the lecture. I'll be happy to review that with you. All right, any questions? So for thionyl chloride, it is the reason why this is specific to primary alcohols is because of this substitution step right here, right? What type of substitution is that based on what I just showed you before we started this? We said that there are two types that you can do. Well, let me not be so general. There are multiple substitution pathways, but I only showed you two a second ago.
Are you talking about the S1 and S2?
What category would this fall into? You can, this step right here where the nucleophile is going to come in and attack your carbon and force your leaving group out. What category would that fall into?
2.
It's SN2. Good. Let me move this over. I don't want y'all to see that later and think that. All right, so this step is I got an arrow down here. Let me fill this in first right quick. I hate writing out the word substitution. Right, so this step right here is a substitution because you're swapping out the leaving group for the halogen, and it falls into the category of an SN2 type substitution. That's why this only works on primaries. It can work on a secondary, but it'll be slower because for SN2, primary carbons are faster because of how it happens, right? With the nucleophile coming in and the leaving group leaving at the same time, the SN2 is much faster on a primary carbon because it's more accessible. So I'm gonna put that here. Right, but we're going to talk about that in a lot more detail when we get to our section on substitution. All right. Question? Any questions about anything? That can be good or bad. No questions either means I did a bang up job explaining it or it's totally foreign. But we're gonna get it. We're gonna meet in the middle. We'll meet in the middle. Let's do the next reaction, right? So the second reaction is to use PBr3 to convert. Again, what we're talking about is converting alcohols into alkyl halides. That's what we're talking about, right? So anytime we're on a topic, always keep in the back of your mind what the topic is so that as we go along, you'll understand like why we're doing what we're doing. All right, so for this reaction, it works on primary and secondary carbons, alcohols, sorry. So it works on primary and secondary alcohols. You normally start out with a 3-to-1 ratio of alcohol to PBr3. All three of these bromines are going to get transferred, right? We're going to loop, but not all at the same time. All right, so we're going to go through the mechanism and you're going to see how this happens. This is again, the bromine here is one of those bromines is eventually going to become my nucleophile to replace the leaving group. Right, so here the first step is this is going to attack here and you're going to lose a bromine. All right, that's how we get to this second step. All right, now this is my leaving group. All right, this is my leaving group. This is what I want to get rid of. How do I go from this intermediate, where I have the leaving group, to the product? What would you do?
Just like the last one,
Mhm.
The bromine is gonna attach to that carbon that's connected to the oxygen
Yes,
because
absolutely.
it's
Say that again.
Oh, just because, like you said, you wrote the nucleophile.
Yeah, so bromine is my nucleophile. It's gonna attack here and kick off the leaving group. Right, that's how we get to the product. So this is my product. This is this step right here going from this intermediate to the product is a substitution. And because it all happens at the same time, it falls in the category of a SN2 type substitution. Right, so it's going to have some of the same limitations as the previous reaction. You know, it prefers primary carbons. It can happen on the secondary, but it's much slower. All right. Now we got to, well, we don't have a problem. We have another concept to deal with. So if you look at what's left, I have my product, but I also have 2 more bromines on the phosphorus. So this can do 2 more reactions. Right, so that's why I said at the beginning, you normally start with a 3-to-1 ratio of alcohol to PBr3. So you have, for every PBr3, you have 3 alcohols that you're going to react with that. So you have a 3-to-1 ratio. Let me cut this out. Put somewhere else. Come back to that. All right. So how would I show that? I'll take another alcohol here. And then I'm going to react it with this. Are you following that? All right, so that's
Yes.
it's just going to come back and do the reaction again, right? So without going, actually, let's go through the arrows. Can somebody put the arrows in for that first step? Anybody? Right, it's the same, nothing changes. Just the reagents change, but the actual mechanism doesn't.
Well, I'm trying. I'm just having difficulty.
It's not working.
Oh, let me see. Okay.
I see your cursor.
Oh, there it is.
That's okay. We'll take that.
Okay. I see. Mm,
Okay.
ooh,
That's all right. That's all right. We're good.
and then from is that a bromine at the bottom?
That's OH. Remember, we're starting from here. Right. So that's going to come. Now you can do that reaction. Let me get that lined up again. Now you can do that reaction again.
Okay, so we're starting from there. So
Yeah. So we're still going to kick off a bromine. We're still going to attack phosphorus
okay,
and still lose bromine.
and then it's gonna be bromine is now detached. Okay.
But you got to show it.
Okay.
You got to show the bond breaking.
So then this needs to go here.
Yes, we can do that one. Yep.
See, it's difficult. I don't know why.
That's okay.
But what I meant to do was take that bond and
give it to that.
yeah, that's what I meant to do.
Okay. All right. You're 100% correct. So now this is O P B R O H, and then this is also OH plus. This is positive plus Br minus. Is that right? That's what those arrows. Let me see if I can line that back up. That's what those arrows indicate. There we go. That's close enough. All right. So now what's the next step?
Now the bromine has to attack the carbon bond that's attached to the oxygen.
Yes. So let's do that.
So do you just go until there's no more bromine attached to the molecule?
Yes, that's exactly right. That's why I was saying you need 3 alcohols for every 1 PBr3, because you use up the bromine. You have to use up every one of those bromines.
Okay.
So this is coming here like that, and then I'm going to lose that. So now I get another product here, another alkyl halide plus POH, OH, BR. So now, obviously, I could take this one and do that reaction one more time. Is that right? Because I still have 1 bromine left. All right, so I can go through that process again and use up that last bromine. So I'll end up with, and I'll just put a coefficient out here. I'll end up with 3 of these alkyl halides. And again, the purpose is to make alkyl halides from alcohols. So I started with an alcohol, I treated it with PBr3, and in my product, I got an alkyl halide. So this is my alkyl halide. All right, any questions about that?
I was just about to say something about that.
Oh, yeah.
No, just that it was, yeah, where you ended off is not where, the last thing on the paper
Right.
is not the same. So you wanted us to do that ourselves.
Yeah, so take this one plus another alcohol and show the outcome and the mechanism.
Okay.
Mhm. All right, now down here, this is just an example of, we have a product and no start material. So the question is, what did I start with to get here? Look at the product. It has a bromine at 3 different places and POH3. So what did I start with in order to get here? What 2 start materials? And why is this
And
easy? Go ahead.
I was gonna say, you could probably tell from the OH that you started with an alcohol.
Mm-hmm. Because again, if you look up here, when we start with PBr3, when we go through all 3 of those alcohols, you eventually you're going to end up with POH3, right? So if you look right here, if this is one of your products where you have 3 hydroxyl groups on that phosphorus, that means that you had to have 3 hydroxyls here in order for those bromines to substitute like that. So what would the starting material or materials look like? Right, we know we start with this as one of my start materials. What does the actual alcohol look like?
308. Well,
The rating is not going to change. I think if we put a OH here, then we need 1 here and 1 here.
oh, that's crazy.
Yeah, but wouldn't it give us the product that we see?
Yeah, that would.
Yeah. So because again, the ratio of PBr3 to alcohol is going to be 1 PBr3 to 3 alcohols. But the 3 alcohols in this case are just all in the same molecule. They're not 3 separate alcohols. They're all in the same molecule. So that's the only difference. But the ratio is always going to be 3 alcohols to 1 PBr3. So if you have an instance like this, where you have 3 bromines that are on that structure with a phosphorus molecule, well, POH3, then you can work backwards, because you know that POH3 is a product of converting an alcohol into an alkyl halide using PBr3. Right, anytime you see that, then you know that that came from PBr3 reacting with 3 alcohols. All right, any questions about that mechanism or the reaction itself?
No, sir.
All right, we got time to finish this part of the handout. We can finish the mechanisms and then we can do the rest of it. Finish it on Monday. Coming up, remember, if you haven't checked the syllabus, the first exam is on next Friday on the 16th. But we're still going to have class because the exam itself is going to be housed on Blackboard. So I'm not going to cancel class for you to take it. You can take it over the weekend between Friday and Sunday. But we'll talk more about that the closer we get to it. All right, let's go back to here. This is the last of the methods that we're going to discuss. Obviously, there are many more methods for doing this, but these are the 3 that we're going to talk about. All right. This one involves using HX to convert alcohols to alkyl halides. This is specific to secondary and tertiary alcohols. You can't use HF. That doesn't work. All right, you can use HI, HCl, or HBr. But the fluorine is not a good enough nucleophile. It's actually a terrible nucleophile. So it doesn't work with this particular reaction. All right, now let's look at the overall reaction. It's a substitution just like the other ones, but it's a different type of substitution because in this case, your leaving group is going to leave first before your nucleophile attacks. All right. So how do we get from these 2 star materials to here? And I should have put it over here. It's all the way over there, but there's the iodine here. So how do we do that? Look at the intermediate and tell me how we could get to that intermediate from the 2 star materials on the left.
So on the left, the OH, the alcohol, but the OH attacks the hydrogen in the what did you call the something, a HX bond or
And then you break the hydrogen iodine bond, give those electrons to iodine. Good. So that gets me to here, right? Which is, that achieves one of the more important parts of the reaction, which is to make the OH a better leaving group. OH is not a good leaving group. And so now this is what we call hydronium ion. Very excellent leaving group. The way you can tell the quality of a leaving group, and I know I'm jumping the gun because we're going to talk about this again, but there's a way to tell it. You look at the pKa of the conjugate acid, right? A low pKa and that's going to be a good leaving group. High pKa, sorry about that. It's going to be a poor leaving group, right? So I need somebody to look up the pKa of water, right? Because if OH is the leaving group, water is the conjugate acid.
You said the pKa of water.
Mhm.
Um,
It says 15.74.
We're going to say 16. We'll round it up to 16. All right. Now, somebody look up the pKa of, so if water is the leaving group, then the conjugate acid is going to be a hydronium ion. So can somebody look that up? H3O pKa is going to be very, very different from water by itself.
L 1.7.
Say that again, 1.7?
Yeah.
Okay, this is good. So that's a difference of, let's say 14.3. So the hydronium is 10 to the, we're going to round that up, 10 to the 14 times more acidic.
Can I ask a question real quick?
That's sure, please.
How come we didn't round up to 1.7?
To 2,
Yeah.
we can.
Oh, okay. I just
But because the top number is 2 sig figs, then I just kept the bottom number as 2 sig figs.
okay.
Yeah, that's all. Right, but between those two, there's a difference in the difference in the pKa is 14.3. And the way you can use that to tell how much better one acid is than the other is just take that number and use it as an exponent for 10. So that's the number of times more acidic one acid is than the other. Is 10 raised to the difference in the pKa. So it's 10 to the 14 times more acidic. And that means that H2O is extremely vastly superior leaving group to OH. That's the only point. That's the only point I'm trying to make. Right. So again, the first step in a lot of these reactions is to make OH a better leaving group. I think that's a quiz question on one of the YouTube quizzes. Right. That's the first thing that you need to do before you can substitute it. So now I've substituted. Well, I have done in the first step, a proton transfer, right, to make the hydronium ion. Right now, instead of the iodine attacking or the halogen attacking, how do I go from here to this carbocation intermediate? What do I need to do? Ooh, we got a minute left.
the bond with the oxygen and carbon.
I need to break it, don't I?
Yeah.
And anytime I break a bond like this, and this goes back to part 1, when you break a polarized bond, the electrons always go with the more electronegative atom. So that's how I get to the carbocation. This is why this method only works on secondary, tertiary alcohol, because of that intermediate. Because a primary carbocation is the worst, one of the worst carbocations that you can make. All right, I'm gonna stop here because if I keep going, then it'll be 10 o'clock, and I need y'all to get to your next class on time. So any questions before we log out?